functions. A linear function is an algebraic function that forms a straight line in a coordinate plane, or you can say on a Cartesian plane, okay? So this is the equation or the formulas that you can use to represent your function. As you can see, this is the f at x. One could say h at x or g at x, it depends, is equal to m at x plus b, or you can say c is your b. Your b or your c is the y-intercept of the graph, and the x, it is the independent variable, which it is your x variables on your graph, and the m, it is the slope of the graph or the gradient of the graph. So this one, it is a dependent variable, which is your y values on your graph. So this is the other equation that you can use, but this equation, it is only applicable if you have 1 point and you are given the gradient. So you can use this formula to find your gradient, which we take the bigger value and subtract your y value and subtract the smaller y value. You divide it by your bigger x value and you subtract the smaller x value. So this is the impact that your m, which is your gradient, can have on your graph. When your m is greater than 0, your graph is going to increase. Hence, it means that your gradient is positive. That's why your graph will be an increasing one. And when your m is less than 0, your graph is going to decrease. Hence, your gradient, it is negative. So when we talk about the domain and right, when we talk about the domain, we talk about the x values. It's actually where the graph starts from your x-axis to until where it ends, and the range, it is where the graph starts from the y-axis until where it ends. So looking at the linear graph, looking at this graph it starts here. It doesn't start here, hence it has arrows. It means that this graph, it starts from the last number of the negative until the last number of the positives. Hence you can say it starts from the negative infinity to positive infinity, or you can say your x is an element of real numbers. Your real numbers is all the numbers from negative to positive infinity, and same applies to your range. It starts from the negative infinity from your y values until the positive y values to your infinity. Hence you can say y is an element of real numbers, even here and simple. Now let's do these examples together. Let's start by finding the equation of our graph. Now this is our mother equation, y is equal to mx plus c. So our c is our y-intercept. So as you can see that this graph is passing through our origin. So you can say your y is equal to mx plus c. C, right? So y is equal to mx plus 0 because your c is 0 because your graph is passing through the origin. Now your new equation is going to be mx. This will be your new equation. So after doing this, you can find your gradient by just choosing any point here and substituting here, or you can use the normal formula of finding the gradient. But let's just choose any point here. So let's just substitute point 2 into the equation. Now you're going to say 2 is equal to m into 2, and 2 is equal to 2m. You divide both sides by 2 because you're solving for m. So your m is equal to 1. This will be your gradient. And another alternative method is that one of finding a gradient is m is equal to the change in y divided by the change in x. So right now you're going to choose another point. You can choose 2 and 2, 1 and 1, 0 and 0, and this other point. You just choose any point. So we can take 1 and 1 and take 2 and 2. Now, since our equation is change in y divided by change in x, it means we're going to, for change in y, we're going to take 2 and subtract 1 divided by our change in x will be 2 minus 1 again. So 2 minus 1 is going to be 1, and 2 minus 1 is going to be 1 again, and 1 divided by 1 is 1. So you can see that our gradient is the same. So it means that when your equation is going to be y is equal to, you substitute your gradient's value, which is 1x plus 0. So you're going to say y is equal to, you can write this one, you cannot write it, it's fine, y is equal to x. It means that from your graph, your x values will be the same as your y values, of which it makes sense because y is the same as x. Let's do our second example. As you can see, this one is a little bit different from that other one. So our first question says we have to find the gradient of our graph. So we're going to use our usual formula, which is m is equal to our change in y divided by our change in x. Now we can choose any 2 points from the graph. So we can take this point and this point. So let me write them down. Straight and gray, 6 and 1. So it will be our m is equal to minus y at a divided by so now I can take this, now we can substitute, right? So it's going to be this y value minus this y value. So it's going to be 1 minus 3 divided by 6 minus 3. So it's going to be minus 2 over 3. Okay, so our gradient is negative 2 over 3. It is negative because our graph is a decreasing one. It means our gradient is less than 0. So now the second question, it says we have to determine the equation of the graph. I think it's going to be easy because now that we have our gradient. So we're going to write our equation, which is y is equal to mx plus c, right? But how about this time we spice up things? Let's use a different equation, this one. Y minus y1 is equal to m into x minus x1, okay? So you're going to choose any point again from the equation. We can take this one, this one, this one, or either this one. So let's take 3 and 3, right? So we're going to substitute 3 and 3 into this equation. This one remains, this one will remain. You will only substitute your point here, okay? So you're going to have y minus 3 is equal to your m, which is negative 2 over 3. You write it negative 2 over 3 into x minus 3. Calculator, guys. Y minus 3 is equal to minus 2 over 3. And negative 2 over 3 multiplied by negative 3 is going to be positive 2 because it's negative times negative will give us a positive number. So you're going to say y is equal to minus 2 over 3 x plus 2, and then this negative 3 will come to this side. It means that it's going to change a sign, it will become a positive. So it's going to be y is equal to minus 2 over 3x. 2 plus 3 is 5. This will be your equation.
Greetings, my name is Mr. Makuni. Today I'm going to be dealing with quadratic function, also known as parabola. So as you can see here, quadratic functions is based with multiple equations inside of it. The first equation is known as the general equation, where f of x equals to ax squared plus bx plus c. Then therefore, the second equation is known as the standard equation. As you can see here, f of x equals to a into x plus p, those brackets squared plus q. Then therefore, The third equation, as you can see, is the equation that is used to determine the value of A. When you have in some points on the graph of that you might be containing, then A determines the direction of the graph. And by saying that, when A is greater than 0, the graph on the Cartesian plane increases. And when A is less than 0, the graph decreases. Furthermore, the P and Q on the standard equation represent the turning point, also known as the vertex. And also, the C on the general equation is known as the constant or the y-intercept. Furthermore, there's also another equation that is used to determine the value or the x value on the turning point, which is this equation here, where x equals to negative b over 2a. Then therefore, let's go to the graphs that summarizes the theory of quadratic function. So as you can see here, these two graphs here, parabolic graphs, are the one that represent or summarizes the theory of quadratic functions or the parabola. As you can see, this graph here is increasing, and the turning points that we were talking about, the P and Q, as you can see here, it's on the curve where the graph curves and goes back to where it came from. And therefore, the A for this graph, A is greater than 0. That's why we say the graph is increasing. And also the domain for this graph, as you can see here, ranges from negative infinity to positive infinity. Or it can either be said the x is an element of a real number. The range for this one, as you can see here, ranges from the value that we might be having as q, ranging from q up to infinity. And therefore, on this graph, as you can see, A is less than 0 and is decreasing, where the range ranges from that q, that positive q, or whatever the value of q might be, up or down to negative infinity. And therefore, it can be written into forms where it's known as the interval form or the inequality form. So as you can see here now we're going to be dealing with one example of a graph that is increasing. So as you can see here, the first thing we're going to do, we're going to calculate the value of A. The value of A, for it to determine, we're going to use the equation of determining the value of A, where it is known as y equals to A into x minus x1 into x minus x2. The x1 and the x2 represent the x-intercept. As you can see here, we already have x1 and x2. Here we're going to substitute y and x, we're going to substitute any point on the graph. So any point on the graph, we already have 0 and negative 3. And the x1 and the x2 are the x-intercept. So for y, we're going to substitute this one, which is negative 3 equals to a into the 0. The x, our value here is 0 minus, then we substitute negative 1 into the x value. Then we do that again in the next x value, where we substitute 3. As you can see here, now we multiply. As you can see, this one by this one is going to be it's going to be negative 3a, where our a equals to 1. So we finally found our A. The second question says determine the general equation. When we determine the general equation, we are going to use that same method if we want to, or we can use this method because we now already have A, but we firstly find the point B. But to really not take time, let's just use this same method to continue where you substitute A, then therefore substitute the x values or any point on the graph to determine the equation, the general equation. The second question says calculate the general equation. When you calculate the general equation, you can either use this equation because we already have A, and as you can see, our C is we already have it because it is the intercept. Or we can use the same equation as this one where we substitute the value of A and the x values so that we can determine the general equation. So I say let's use this equation to continue further. So we first, number B, we first substitute the value of A, which is 1, it's going to be 1 into x minus here since it's minus minus, it's going to be plus 1 into, here as you can see, it's going to be x minus 3. So here we calculate going further, therefore we calculate as you can see, this x is x, this x by x equals to x squared, then x by 3 equals to minus 3x, because the negative is always negative when calculated with the positive. Then as you can see here, positive by is going to be positive, because even on the other side is positive. Positive by positive is positive, but negative by positive is negative. So here we're going to be having x. And as you can see here, our value is negative 3. So our final equation, our final general equation here is going to be x squared minus 2x minus 3. Therefore, our final equation, general equation, is f of x equals to x squared minus 2x minus 3. Then now we're going to have to determine the turning point, and we're going to write the equation of in the standard form. Firstly, see the turning point. The turning point, as I have said, since we have the general equation, we use this equation of determining the x value of the turning point, whereby x equals to negative b over 2a. So negative b, as you can see, let me continue here. As you can see, negative b, the b here is the 2. As you can see, the b here, the 2 value here, the negative 2 value here represent the b there. So which means here we're going to say negative into negative 2 divided by 2 into our a is 1 into 1. So our final answer here, as you can see, is 1 again. Our answer is 1. So as you can see here, since we find the x value of the turning point, we're going to now substitute the x value into the general equation. So here we are substituting right now. f into 1. So here is going to be 1 squared minus 2 into 1 minus 3. So here, as you can see, we have to calculate here 1 minus 2 minus 3, which will be, as you can see, negative 4. So, which can be said that our standard equation, or our turning point, let's first begin by turning point. Turning point TP is going to be 1 and negative 4. So we're going to write this in standard equation. In standard equation, it's going to be f of x equals to, here we're going to write x minus 1 squared minus 4. So this is the standard equation. As you can see here, the last question, it says determine the domain and the range. So when you determine the domain and range, the domain, so as I have already said, the domain of any parabola, ranges from negative infinity to positive infinity, which means we're going to write it in interval notation. Then there's the range. The range, it determines by the curve where it tends. So when it tends, as you can see here, the graph is increasing. The point where it tends, it must be equals to or greater than, because this graph is increasing. So here we're going to say the range y, the y value, or let's write it in interval notation. As you can see here, it touches negative 4, it touches the negative 4 and goes up to negative infinity. So this is all the example that I've given. Another example will be coming. Thank you.
Greetings, grade 12 learners. I go by the name of Miss Mtawi and I'll be presenting the hyperbolic function. Some of you may ask, what is a hyperbolic function? Well, a hyperbolic function is a function that is determined by this formula written here. This is the parent formula. All the other hyperbolic formulas come from this formula. So, in simple terms, I can say that a hyperbolic function is y is equal to something over x. This k can be any number, but we have our constant variables which are y and x. Okay, so right now I'm going to try to sketch the simplest hyperbolic function, which is y is equal to 1 over x. Yeah, this is the simplest actually. So I'm just going to try to show you how to sketch a hyperbolic function using this function. Okay, I'm not going to use a ruler or anything, so bear with me. I'm just going to show you how the graph would be if we were given this formula. Our graph was going to be like something, I'm sorry. It's going to be something like this. Okay, our graph, this is the simplest graph actually. Since I said this is the parent equation, it means this comes from this one because our graph can transform into another formula actually, which can be y is equal to k over x plus p plus q. The q value is still the shift. The q value represents the shift. It tells us whether the graph is shifting upwards or downwards. If the graph is shifting upwards, then our q value is going to be positive. And if let me write that down. Q up. And if our q value is negative, the graph is going to shift down. So what happens if our p is positive? If our p is positive in the original equation, it means that our graph is going to shift to the left. And if our p is negative here, then it means that our graph, is going to move to the right. Got it? Got it. Thank you. So k determines the shape of our graph. If k is positive, then our graph is going to lie in the first and third quadrants. Yeah, if our k is positive, then our graph is going to lie in the first and third quadrant. What happens if our k is negative? If our k is negative, our graph will lie on the second and fourth quadrants. Not forgetting that our graph consists of asymptotes. Some of you might ask, what is an asymptote? An asymptote is a line that our graph will approach, but it will never touch it. No matter what happens, no matter how the graph will increase, it will never touch the asymptote. So, okay, on the first graph that we presented here, our asymptotes are 0 and 0 because actually asymptotes are determined by the value of p and q. I hope you're following. Our asymptotes are determined by the value of p and q. So in order for us to find our asymptotes, Q here represents the horizontal asymptote, and then X plus P represents the vertical asymptote. So here, let me just write that down. Our vertical asymptote is represented by 1, which is equals to Q. Then X plus P is equals to 0, represents our horizontal asymptote. Then X is equals to negative P if we were given a formula like this. So actually P represents our horizontal asymptote. So now I'm going to teach you how to sketch a hyperbolic function. Let's say we were given a formula written like this: 3 over x plus 1 minus 2. Using the formula that I gave you here on how to find asymptotes, I hope even here it won't become very hard for you to find them. So you can pause the video for maybe 2 minutes and find the asymptotes, then go back again, because I'm gonna do it for you guys. So our y asymptote here is represented by negative 2, and then our x asymptote, we're gonna find our x asymptote like this, and then this is our x asymptote. So let's move to the next step of sketching graphs. You have to find the x and y intercepts. So for x intercept, let y be equal to 0. Always note that. Then we have our formula. So for x intercept, I said let y be equal to 0. So we're gonna replace 0 where we see y. Then we're gonna have something like this. So then we're just gonna do the inverse of negative 2, which is positive 2. What you do on the left, you also do it on the right. So we're gonna have something like this: x plus 1. And then here, we're gonna cross multiply. Then we'll have something like this one. I'm just gonna take it step by step. Then we're gonna multiply the things in the brackets with 2, and then we'll get 2x plus 2 being equal to 3. Then after, we're gonna group like terms, meaning that we're gonna take these two, we're just gonna make an inverse again of 2. So we're gonna have 2x being equal to 3 minus 2, and then which will give us 1. So we have to divide both sides by 2 so that we can be left with only x on the left hand side, right? Then this is our x-intercept. So let's write the coordinates of the x-intercept. Yeah, these are the coordinates of the x-intercept. So now let's find the y-intercept. For y-intercepts, we let x be equal to 0, right? So here is our formula. Where we see x, we're going to replace x with 0. So we're going to have something like this. And then y will be equal to 3 over 0 plus 1 is equal to 1. Yeah, minus 2. Then 3 divided by 1 will be 3. Any number divided by 1 is that number actually. So we have 3 minus 2, which will give us y be equal to 1. So let's write our y-intercepts as coordinates, and then we'll be having 0 and 1. So this is our y-intercept. So now let's keep all the details that we have, because I think I have to erase here because of space actually. And so I'm just gonna write this somewhere here so that we don't forget. This is our x-intercept, and then this is our y-intercept. Let me write them here, 0 and 1. I'm just gonna erase here. So now let's try to sketch our graph with what we got actually. Oh, I see too. This will be -1, -2, -3. 1, 2, 3. My graph might not be up to scale because I'm sketching using hand actually, so bear with me. Then let's start by inserting our asymptotes first. Then we have our y-asymptote, which is -2. Then we're gonna go where there is -2 in our y-interval, then put these dotted lines. And then our x-asymptote is represented by -1. Then we're gonna go to our x-intervals and find -1. So where there is -1, we're gonna put dotted lines, right? These dotted lines represent our asymptotes. So since another thing, since our k is positive, it means our graph is gonna lie on the first quadrant and third quadrant. Note that. So our x-intercept is represented by 1/2, which is also 0,5. I'm sure you know that. And then our y is 0. So we're gonna go to the graph, find 0,5, which I hope it is somewhere here between 0 and 1. As we say, this represents our x-intercept, our y-intercept, I mean. So we're gonna go to our graph, find a point where x is equal to 0 and y is 1. So I think here is the point. So we're just gonna join these dots. But then remember, our graph doesn't have to touch these asymptotes. So hopefully our graph is gonna be like this. The graph will always approach these asymptotes, but it will never touch it. I hope you see that. Then, since our graph is on the first quadrant, then it means our other graph is gonna be here. I hope you got that. Then let's move to the domain and range. Some of you might ask, what is domain and what is range? Well, domain is the y values on our graph, and then the range is our x values. So, and always remember that domain is our x values and on the graph, and then the range is all the y values we have on the graph. But then the domain and the range of hyperbolic function, I think it is all the same actually, because our domain can be any number, which is our x value. We can represent our domain as x is the element of real numbers, but our x will never be equal to -1. And then mind you, this -1 is our x asymptote. So when it comes to our range, which is our y values, of course, then we can represent our y values as y is the element of real numbers, but the same applies to our y values. Y can never be equal to -2. I think you get what I'm saying. So I'm gonna give you another example which you're gonna do on your own. Y is equal to 4 over. You're gonna use every basis that I gave you actually to solve this one for me, and then you will have to find the asymptotes, B, coordinates of the x intercept, and again coordinates of the y intercept. After you have to sketch the graph. Lastly, find the domain and range. That's all for today. Thank you. I'll pass the lesson to Mr. Kenneth.
Okay, I'm Mr. Mahlangu, and I'll be focusing on the exponential function. As my partners already covered some other functions, this is the one that I'll be focusing on. Okay, it is essential that now we start now. The equation of this function is y is equals to b to the power x. That's the original equation of this function, and the general equation, because the exponential function also undergoes the transformation and translations. So when it has transformed, this becomes the general equation. There are some changes from the original equation. So it becomes y is equals to a b to the power x plus p plus q. Bear it in mind that now every variable in this equation has its own importance, so it has its own effect on the graph. So there are restrictions. So the restrictions for this equation, b must be greater than 0 always. If b is less than 0, it will be problematic for the function because it won't be an exponential function anymore, and b must never be equals to 0 again. So these are our restrictions, and I think it would be better that now we go deeper into details about these variables so that we can be able to see how they affect the original graph. So let's see what's the importance of a in this equation. So a determines the shape of the function as well as the side where the asymptote lies. So I'm sure you are aware that the asymptote, it is the line that the graph does not touch. What do we mean by saying the side where the asymptote will lie? We mean like the graph will be above the asymptote or below the asymptote. That is determined by a, of which is this one in the equation. Okay, let's go forward. Together a and b determine whether the function is decreasing or increasing. You know that now, by now you should be able to know that there is an increasing function and a decreasing function in every fraction. So in exponential function, whether the function is decreasing or increasing, that will be determined by together a and b. We'll look into details about a and b later, what I mean about this one. So about p and q, of which is this one, p and q, they affect the horizontal and vertical shift respectively. Bear it in mind, respectively. I mean p will affect the horizontal shift while q will affect the vertical shift. And q it's equals to the asymptote. So if I'm moving the asymptote upwards and the graph is above the asymptote, also the graph will move away from the asymptote because it doesn't want to touch that particular line. So as I promised that we'll look into this thing in details later. Okay, let's look to it now because I wrote it here, what it means actually. Okay, so we're looking at the effect of A and B, whether the function is decreasing or increasing. Let's start here. If A is greater than 0 on your equation and B is greater than 1, your function will be increasing and it will lie above the asymptote. You must know this. In your heart and in your mind that it is always like this, it won't change. So if A is greater than 0, A is positive, and B is greater than 1, your graph will increase above the asymptote. If A is less than 0 and B is still greater than 1, your graph will decrease, but will decrease how? Below the asymptote. Let's go forward. Let's see now the effect of B thoroughly, because you can see that B here is not changing. Only A is changing and the function changes like this. Let's check the function's behavior when we only change B now, and also A will change, of course, but here we're looking at the effect of B thoroughly. Okay, B is greater than 0 but less than 1. A is greater than 0. The graph lies above the asymptote but it decreases. Understand? When B is greater than 0 but less than 1 and A is still greater than 0, the graph will decrease above the asymptote. And A is less than 0 and B is greater than 0 but less than 1, the graph will increase but below the asymptote. So as you can see here, if you analyze it thoroughly, you'll see that if A is greater than 0, our graphs are above the asymptote. And if A is less than 0, our graphs are below the asymptote. Going forward, let's talk about the domain and range, specifically for the exponential function. So let's start by focusing on the domain. So the domain of the exponential function, it doesn't have any restrictions. So it starts from the lowest number on the Cartesian plane to the very highest number. So which means the graph will touch each and every number on the Cartesian plane. That is why we say it is X is an element of real numbers. Every number that exists on the Cartesian plane, and therefore you can represent it also in the interval method, of which X is an element of negative infinity to positive infinity. Remember, you have to use these brackets because they indicate that now these numbers are not included. Remember, use these brackets. If you use that square bracket, you will be wrong. So going forward, let's talk about range also. Range is a little bit complicated, but don't be afraid because I'm here to explain that. So focusing on the range, we can say, representing with inequalities, we can say y must be greater than q. But there is a rule after that. If a is greater than 0. Remember, if a is greater than 0, your graph will lie above the asymptote, and asymptote is q. So y must be greater than the asymptote, greater than q. That is your range for this graph. First, if a is greater than 0. And you can also represent it in the interval method. Y is an element of q to positive infinity, using those brackets because the graph does not touch q, so q is excluded. So the graph, which means it starts just above q to infinity. So let's check what happens if a is less than 0. So if a is less than 0, your range will be y is less than q, which means your graph will lie under the asymptote. That is why I told you that thing of above and under the asymptote is very important. So y is less than q if a is less than 0. Y is greater than q if a is greater than 0. Simple, né? So you can also represent this thing in the interval method. Y is an element of negative infinity. Remember, when you represent this thing in the interval method, you have to use like the smallest number first to the biggest number. Remember, infinity, we don't know what's the last number that the graph touches. So it's the biggest, this one is the smallest. So negative infinity is the smallest, this one is the biggest. Remember to use this bracket. It is very important because they will put you wrong if you use the square bracket. So let's go forward and do maybe a little bit of example. I won't be focusing on examples today. I just want to test your knowledge. Please try to pause the video for 2 minutes, 3 minutes and try to do this. So here, what you are supposed to do, the question is, you have to sketch this graph and test your limits, whether like you can be able to sketch it after your prior knowledge from previous grades and after what I have taught you here. So try to pause the video and sketch this graph. But me, for my sake, I will try to sketch it now so that we can save time. But you pause the video. Okay, so sketching this graph, okay, so after sketching the graph, try to determine the domain and range. Here, as I explained, you have to sketch this graph. So for you to be able to sketch this graph, you have to find first the x-intercept of this graph. So for finding the x-intercept, you have to make y to be equals to 0, of which you're going to take this y and substitute here, which means 0 is equals to 2 to the power x plus 1. After this, you have to transpose this one to the other side, and this one, the sign is going to be change. It's going to be negative 1 is equals to 2 to the power x. And negative 1 cannot be equals to 2 to the power x. If it was 1, we're going to be able to solve this thing because we're going to apply your algebraic skills. So from here, you can be able to see that this answer is invalid, so you can say no solution. Which means this graph is not going to touch the x-axis. And that's possible. That's possible because remember, it's above the asymptote because our a is greater than 0. And remember, this thing, it's an asymptote here. So which means it went further upwards a little bit. So it's away from the x-axis. So no solution. We do not have the x-intercept. Let's look for the y-intercept very fast. So looking for the y-intercept, we do the opposite. We make x to be 0. So for y-intercept, x must be equals to 0. Simple, né? So y is equals to 2x plus 1. Remember? So if we do this to be 0, y is equals to 2 to the power 0 plus 1. Remember, any number to the power 0 is equals to 1. So y is equals to 1 plus 1. And our y-intercept is equals to 2. So, gathering this information, we are able to draw our graph. Very simple. We are able to draw our graph, to sketch it. So let's sketch this graph very fast, very fast. So we can draw our little Cartesian plane there. Doesn't matter, you cannot draw it to scale as long as you are able to see what you are doing actually. So we know that now I said this is Q. So Q is our asymptote, which means Q is somewhere here. It's somewhere here. Q is somewhere here. So this is our asymptote. Where does Q cut? Q cuts y-axis at 1. Q cuts the y-axis at 1. Therefore, our graph is an increasing function above the asymptote, which means it's going to go like this. Like this. This is our exponential function. This is the y-axis. This is the x-axis. And where does it cut? It cuts y at 2, which means our point here is 2 and 0. This is 2. It's 0 and 2, sorry. 0 and 2. This is 2. This is how our graph goes. So, I'd like you to check yourself whether like you were able to come with something like this and to determine your range and domain thoroughly such that you got your answer correct. So if it's not correct, check where did you do your mistake. So let me try to determine the domain and range for this function very fast as I'm finishing my video because like time is not in our side. So in the commenting on the domain of this function, you can see that this function is starting from negative infinity. This arrow indicates that this function goes and goes, that goes up until the last number, and it goes still that way up until the last number. So we can say our domain is x is an element of real numbers. You can also represent it in interval notation, as I told you how to represent it in an interval notation. So this is our domain. I hope it's visible. Sorry, I don't have space. So this is our domain. So our range. So range, it can be dangerous in this manner because if you don't know what is your asymptote, the range can be wrong. So look at this thing. Q is an asymptote. I'll represent it using the inequality notation. You can do yourself the interval notation and see where you get it right, because if you see how I do this one will be easier. So y for domain has to be greater than q, and in this manner q is 1. This is our range, this is our domain. I hope you found this lesson very interesting and you learned something from us. In the next video, we'll be focusing more on the inverse functions and we'll be doing more examples for the functions. Thanks to me and my team, I hope you got it right. Thank you, I'm Mr. Mashao.